All right, thanks everybody. So I thought I'd talk a little bit about the work that I'm doing, some of the research, which is aerodynamics. Most people have heard about aerodynamics. Most things that you travel in, see, cars, bikes, planes, are shaped because of our understanding of the way that the flow moves around it. And for me, high-performance computing, HPC, has just opened this up to a whole new level. And I kind of think it's interesting to explore it a little bit. So, why aerodynamics? Well, if you think about it, planes are flying through the air, therefore we want to understand how the flow moves around the object. And the reason it's important is that now the aircraft industry is having these huge pressures to make more efficient, more green aircraft, to make it quieter. Right? Has anybody living near an airport, or has ever lived near an airport? It's a real distraction. They're coming in, and if they want to open it up later, more hours, then you've got to reduce the noise of these things. And most of the noise is coming from turbulent flow around the aircraft, and so we need to understand it more. The other one is obviously just saving fuel. Most airline companies, their biggest cost is on the fuel. Right now, the price of oil is pretty low, so maybe they're not so worried about it. But if it goes back up to the way it was before, then they will. And interestingly, for me, the electric aircraft, and you can go over to the NASA stand and see one of the X-planes they're working on, and they're going to really need to make this low drag. They want to make this as efficient as possible because they need to ultimately power this with batteries. Same thing, cars. One of my many areas is on cars. This is, I don't know if you like the Mini, this is going to be the electric Mini. So this is going to be built in Oxford, and it's going to be, I think, pretty popular. The US as well is loving this car. And the thing with electric vehicles is you need to have the least drag possible, that resisting force, because you can only fit a certain number of batteries in a car like this. So you've really got to come up with some new innovative ways to reduce the drag, make it more efficient. So how do we do that? Well, one of the interesting things is you can either do simulation or physical testing. You can actually fly a plane through the air, you can drive a car, or maybe we can actually use simulation, which is the way that things have progressed over the past 30, 40 years thanks to high-performance computing. So let's try and compare them. So you've got experimental methods. So we could, this is a case of a bike, we could put it in a wind tunnel. So instead of cycling through, we keep it still and we blow the air over it. And we can try and understand what's going on, the forces around the bike. Well, we can actually use a real bike, a real person, so it's pretty accurate. But the problem is it's expensive because you've got to make that thing first, and you've got to get somebody in there to do it. And if it's a plane, and it's a new prototype plane, to build a whole plane and put it in a wind tunnel is pretty expensive. So the other one is we could use computational fluid dynamics, numerical methods. So I'm not going to go into the details of this because that's going to switch people off pretty quickly. But essentially it's like a virtual wind tunnel where we can solve the Navier-Stokes equations, and essentially it's pretty much correlated to the size of the grid and to the size of the HPC system that you have. The main advantage is you don't need to make anything. It's all virtual. You can just sit down in your bedroom, draw this bike, and run it, if you have a big enough computer to run it on. But the problem is accuracy. And that's really the bottleneck at the moment. Now, I want to go through a couple of examples of where CFD is really important. And one of the best ones is this car. So this is the Bloodhound, which is aiming to beat the land speed record to go 1,000 miles an hour. This is a pretty beast of a car, about 10 meters long. It's got a fighter jet engine in from the Eurofighter and a rocket. Now, this is going 1,000 miles an hour. This is some of the work we do in collaboration with Swansea and Bloodhound. Anyone who knows about wind tunnels, I don't think there's a wind tunnel around, not even at NASA, who could put one of those in and with a moving belt, because the wheels are moving. So you can't do this experimentally. You can only do it in CFD. Or you could say, let's make one. But when they're prototyping, I don't think you'd want a guy or a girl to drive this at 1,000 miles an hour when you're trying to figure out how it works. So this is an example where CFD is a necessity. But I thought one interesting thing is to actually look at some of the costs, because people always say CFD is cheap compared to doing a wind tunnel. So we're just going to use a computer and it'll be fine. So I thought, let's figure this out. So if anyone's into like Formula One or motorsports or racing, this is a pretty good example of if you want to develop a car. So you've got 8 weeks of testing. Right? You're going to create the fastest, the best car you can. And the blue curve is the experimental method, and the green is CFD. And I'm going to say low fidelity CFD because one of the themes that my research is trying to do is to bring more accuracy so that we can get rid of this experimental method. So let's look at these numbers. First of all, it's a pretty big number, £500,000 over 8 weeks. That's why Formula One and NASCAR and IndyCar spend so much money. And CFD is down here. So let's look at it. It costs quite a lot of money to make the model, £75,000. You've got to make this thing, you've got to instrument it, put in a wind tunnel. And then you've got to hire a wind tunnel, and you've got to make parts for it. So if you work out the numbers, I'll leave you to figure out if I've done the sums right, then you get out to this cost. If you do it in CFD, you don't need to make anything. You need to maybe get somebody for a week to make the mesh, and then you've got to run it. Now, we're assuming here everyone's just using hired facilities. So this is a wind tunnel hired and a cloud facility. So I've just got a number here, which a pence per core hour, which you can take from any cloud computing company. So you can see it's really cheap. You can see why if you can just do CFD, you can save hundreds of thousands of pounds, which is why everyone's doing it, and why Lenovo's probably making so much money from selling these HPC systems. But then the interesting thing is the accuracy. So this is some of the work that I've been doing with an OEM, and it'll be more details at the SAE conference in next year. But what's interesting, so this is a car, an actual production car. I'll leave you to guess what brand it is. And we can see here the drag and the lift. The main point is this yellow is the low fidelity and the blue is the high fidelity. I'm blocking out the screen here, but you can see this basically is the difference between the error. That's a huge error. So it means that you can't use this method to design a car. It's not accurate enough. So you've got to go in a wind tunnel, you've got to spend those hundreds of thousands. But if you start using these high fidelity methods, then you can actually start to bring this accuracy so close that you could potentially start to do away with wind tunnels. We're not there yet, and we need more methods, more research, bigger machines, but this really gives the idea for it. Now you put the line back up on there, and you see, actually, this high-fidelity CFD is not that cheap, and starts to bring it closer and closer up to the line of doing experiments. And this is why it's not so simple to say that doing simulation is always better than experimental methods. And you can work out the cost simply because it's a transient simulation, you have to do it in time, and if you've got to now run it for maybe 48 hours instead of 4, that number pops up to be pretty big. Now, the caveat with this is this all depends on your numerical methods, your CFD, your cost of your wind tunnel, all those things. But I think the switch between the low and the high is pretty reasonable. And that's really where HPC is the king. And I always show this picture because this is my Nostrum, which is, I think, a Lenovo machine. But it's a pretty nice machine. And that's really the bottleneck, HPC. The example I give all the time, because I used to work in Formula One, and I think it's the best example of ultra-time sensitive, aerodynamics-driven sport, where they need to get something as quickly as possible, and turnaround time is key. That's because in 3 weeks, they can go and design an entire new part from just an idea in someone's head, sat down at a keyboard, going all the way through the process from CFD to a wind tunnel to the simulator to actually a track. And that's 3 weeks. So they can't afford a simulation to take 1 week if they're meant to have already started manufacturing it a few days before then. So this is a really good example of one where it's time critical. Now, at fear of showing too many numbers, I hope there's some people here who have a broad interest in CFD, and you might get into this a little bit more. If you're not, I do apologize. But this is an interesting stat that shows why HPC is king. So this is a low fidelity. These numbers are pretty realistic. About 4 hours to do a simulation. That's why they can do it in 3 weeks, because it only takes 4 hours to do a whole simulation of a whole Formula One car. But if you want to do the high fidelity methods, you're going to jump to about 120 hours, based on the grid, based on the number of hours that it's run. And the main reason is because it's transient. But this is only, now this is going to the HPC side. We're only using 512 cores here on 240 million cells. Anyone here with a HPC background can work out that's actually not that many cores. So what if we go down to 50,000 cells per core, which is probably reasonable scalability for quite a few codes? Could we now use 4,000 cores? And if we assume a linear scaling, which of course it never will be, but let's just assume it for the maths, it comes down to like 13 hours. So we're starting to get closer, but only if you have 4,000 cores available to you. Now, the problem is 13 hours is still too long for some people. They still want it down here. So this is where we do need still new methods, which I've listed here, and I'm not going to go into the details, but there's a lot of interesting research on trying to really break this number down to bring it into the industry. And luckily, you're really close to the NASA stand, and some interesting work in these areas going on over there. Well, the final kind of stumbling block maybe is right now, if you're a Formula One team, you run on 500 cores for a typical simulation, and you have 20 people doing 2 simulations per day each, so about 40 simulations a day. So you need about a 20,000 core cluster, which is reasonably sized for a big automotive company or for a Formula One team. But if you want to run 4,000 cores for all your simulations, then you need a cluster of 160,000 cores. So this is where the interesting debate on would they want to have 160,000 cores, or is this the real proof that they need to be moving into the cloud because to have that on-premise is just not realistic? So really, what I wanted to try and show you is the reason why we're doing some of the CFD. I put this picture up because really this is to show that even though we look at HPC being expensive, and potentially too expensive, the competitor is still these type of wind tunnels, which are absolutely massive and use a huge amount of power. So maybe investing in big HPC facilities is still cheaper than building these big wind tunnels. So really, this is where the research is going on now. Can we bring this turnaround time for industry to actually use these methods to make the more efficient planes and cars of the future? And really, HPC is the key for that. So thanks very much, and just a quick thank to the ARC guys, a couple of people here. This is because this is the Supercomputing Centre at Oxford, which I'm constantly emailing them and asking for more hours and more runtime. So I feel that they definitely deserve a thank you on that. So thanks, Steve. Dr. Neil Ashton, everyone!